By Michael Shearer from North Carolina State University, who's going to talk to us about continuum models of two-phase flow in porous media.
Thank you, and thanks to the organizers of the CFM program for inviting me. It's very nice to be back in Cambridge, and am I supposed to do something? Oh, I'm supposed to turn it on. Yes, that's right. One simple instruction, which I forgot. Okay, better? All right. Yeah, so very nice. Last time I was here, actually, I spoke about two topics, on granular materials and then on thin liquid films. So this is a different topic, which I've been interested in for a while, and got interested in again just a few years ago. So I want to tell you some new things on this topic. So there are various, I probably won't get through the whole talk, but let me mention contributions from various students and former students, and then recent collaborators, Ruben Juanes and Luis Cueto Felgaroso from MIT, who actually heard my student Kim Spade speak on flow in porous media and got very excited because of a project they were interested in, which I may get to at the end or may not. Rachel Levy is now a faculty member at Harvey Mudd College, and Melissa Straight is a current graduate student at NC State, working on the project with Ruben and Luis. Zheng Zheng Hu is a postdoc at NC State. She's just about to set up her own company in education, so she's becoming an entrepreneur. So here's a quick slide on various applications. My focus really is on secondary oil recovery with water flood. So here water is pumped down a well to force oil out of a remote well. And this picture actually is somewhat faithful in that there's all oil near the remote well. There's a sort of intermediate zone, a mushy zone, if you like, which we'll interpret as a rarefaction wave, and then pure water behind. Now, of course, you don't displace, this suggests you displace all the oil in the reservoir, which is far from the truth. There's also there are similar models for water infiltration under gravity, although what I'll discuss neglects gravity. The interesting thing about these plots is that the water saturation, the volume fraction of water in pore space against vertical distance, is not monotone in many of these volumetric flows. And then I won't get to this topic, but similar models applying carbon sequestration with some interesting differences actually, because you're depositing one of the fluids, and so actually the conservation laws have a discontinuous flux. So we're working on this topic, but I won't get to it in any detail. All right, so there's a somewhat extended introduction to give you the framework, some of the early equations, and the models I want to discuss. The basic framework for continuum models is to write down conservation of mass and replace conservation of momentum by Darcy's law. We'll also assume that all the fluids are incompressible. Even when there's gas present, you assume the flow is slow enough that you can assume incompressibility. So the classical treatment was by Buckley and Leverett for two-phase flow, and they get a flux function f of u, where u is the saturation, so the saturation of one of the fluids, say water. And so the most primitive equation is just a non-convex conservation law, so a nonlinear equation. Now, there is an important piece missing here, and that is the pressure difference across the interface, and that's called the capillary pressure. It's associated with an interfacial energy, and the classical approach from the 50s and 60s was to assume that pressure equilibrates on a very fast time scale. So you take the capillary pressure, Pc, to be the equilibrium pressure and assume that it only depends on the saturation. If you do that, then you get, so it's reasonable to model this as a decreasing function, although there are models where it's not decreasing. And you get a single parabolic equation. It's actually degenerate because h is 0 and 1. So what we're going to look at, actually, I'll tell you a little bit about this equation, but I'm really interested in this equation formulated by Hassan Izzadeh and Gray in the early 90s, which adds a rate dependence to the capillary pressure. So there's a relaxation timescale tau and just a simple rate dependence. This is actually a gross simplification from what they have. They have all sorts of mysterious constants in their paper. The Netherlands group, I learned about this model actually, even though Gray and Hassanizadeh were at the time just down the road at UNC Chapel Hill in North Carolina. I first learned about this model from Bert Pelletier, and they had actually done a lot of work. There's a whole group here, Pop, Van Duyn, Pelletier, Cuesta, and a graduate student, Fan, who wrote a very nice thesis last year on this Hassanizadeh and Gray model. So I want to tell you a somewhat different approach to this model from the Netherlands group, and more or less a complete story about primitive waves.
So if you substitute in your sub E there,
Put PC in here.
into there,
Yes.
that makes that equation non-local?
It makes the equation dissipative and dispersive, actually. So we'll come to this, Daryl. You'll like this. There's a UXXT. It's like a
Right, so
BBM
it's a
term.
regular, if h of u would be constant, you move this to the other side, would have a nice regularizing.
That's right. Yeah, indeed. Right. So we're not going to do that, but and Fan didn't do that either. His analysis is based on finite difference approximations. But yes, you're right, that it's a very weak dispersion. You can use it as a regularization. Okay, so then I want to talk about two-dimensional stability and instability for lax shock. So this is all at the hyperbolic level, except that in fact we make the system large, we make it into a system, and it's really a hyperbolic elliptic system. So the shocks themselves are, of course, for the hyperbolic equation. But the last part of the talk, I've got 46 slides here, as you can see. You can even keep track of where we are with this software. The last part of the talk is a phase field modeling. So a different approach to modeling flow in porous media, and is really a more based on the energy functions, and gives a PDE which is a fourth order, not a second order, more like a Kahn-Hilliard equation. So there are similar models of earlier models of Juanes, Wittelski, and even de Gennes, which I'll mention later on, to do with polymer mixtures. So the context we'll look at, or maybe not look at, maybe I'll just throw up a couple of slides, is gas displacing a fluid in a capillary tube. And then actually Juanes and the postdoc Luis Felderoso have extended this to a Healy-Shaw two-dimensional situation. All right, so we will focus on traveling waves, and there's actually an interesting dynamical systems issue, because the traveling waves don't go from minus infinity to infinity, they terminate at a certain point, and so there's this trick for analyzing them. I mentioned carbon sequestration and the discontinuity in the conservation law. Okay, so here's the two-dimensional model, a simplified model of two-phase flow in a porous medium, so just 2 dimensions, not 3. And the variables are just the saturation and the pressure. So the saturation in one of the phases, so water, and the pressure in water. So 1 minus U will be the oil saturation. We'll write down conservation of mass with Darcy's law. So here's Darcy's law. The velocity is proportional to the pressure gradient with a mobility constant that depends on the saturation. So it's not really constant, the mobility coefficient. So we put this velocity into conservation of mass. This is just mass transport with a porosity which will normalize to 1, if you like, by changing the time scale. And then the mobility is related to the viscosity mu, a relative permeability. So there's one for both water and there's a different one for oil. An absolute permeability, how receptive is the medium to penetration by a fluid. The relative permeability is a fraction of that permeability for each of the 2 fluids. Incompressibility says that the total velocity, right, so this is a mixture theory, the total velocity is divergence free, and the total velocity, after you do a bit of algebra, it has this expression in terms of the variables u and p. And so here I've written the capillary pressure as a function of u, just to emphasize that we're going to make this give an equation of state, if you like, for PC. Right, so I'm going to use some other notation here. There's a total mobility, just the sum of the two mobilities, and the capillary pressure is just the jump in the pressure across the interface. So the pressure in the oil minus the pressure in the water.
Don't you need incompressibility for each phase separately?
No, because it's a mixture. It's the so I don't know quite how to explain that, but it's really regarding the two-phase flow as a mixture of two fluids, and it's the total mixture that is incompressible. So the two velocities separately are not divergence free.
How about boundary conditions for P?
So we're going to pose this everywhere. I mean, I'm just looking at shocks and traveling waves.
At infinity then?
At infinity, right, yes.
So
we'll look at bounded solutions. That's the only restriction.
Not enough. So you want P to decay at infinity? P not...
Yeah, P actually, we'll see that P will grow at infinity. It's going to be linear because it's related to a velocity which will be constant on each side.
Well, I'm just worried about then inverting, so you have a free constant then. That's okay.
Yes, because it's only the gradient of the pressure that comes into play. That's right.
Sorry, and the total velocity is just the two velocities weighted with the two concentrations?
They're just added together. There's no weighting in the total velocity. They're just added together.
It's not mixture theory then?
Yeah,
because mixture theory, you weight the two velocities.
Right.
The
There's a lot of normalization I've done here actually to simplify it, so we don't have lots of
comes back
constants.
to this.
Yes, maybe that's right. That there's right. So if it's mixture theory, I agree. You scale by the densities, for example. Yeah, that's true.
But another question there.
Yeah.
Capillary pressure, I mean, your U is defined everywhere,
Yes.
but now this capillary pressure is also defined everywhere. So are there
Yes.
interfaces everywhere? So it's the interfaces between the two phases?
Yeah. So I make no excuses for this model. It's not. There are lots of things that are wrong with it. So and I'm sure we could get the petroleum engineers to criticize it very well. But this is the classical model that has capillary pressure defined everywhere. So you can think, if you like.
It's not a big pressure. It's not the gradient concentration times gradient concentration in a. I mean,
Think of oil with bubbles of water in it. So there's interfacial pressure everywhere,
Okay, so it's local. Yeah, I see.
locally defined. All right, that's right. So that's the. I mean, I was thinking of capillary pressure as being, that you've got a sharp interface between oil and water, right? That's what you like to think about. That's the approach of Juanes and Cueto Felgarosa. And that's why I think their model makes a lot of sense for this displacing one fluid by another fluid. But in this context, we're assuming there's oil and water everywhere. And the capillary pressure, as it depends on U, has limits as U goes to 0 and U goes to 1.
Well, it's very reasonable because there are pores of different sizes.
Right, yeah. Well, there are pores of different sizes and there are different mixtures everywhere. You're not displacing all the oil. So it's not just a single interface.
So where K of U does vanish, are you going to tell us if K of U ever vanishes, little k or big lambda?
I'm going to tell K of U is a convex increasing function in both phases. So in our simulations, it'll be quadratic.
And the minimum is not 0. Or is
The minimum is 0. Yeah.
Okay,
yeah,
so
yeah.
there is a
Right.
degeneracy at 0.
Yes. Okay. Right. So the one-dimensional equation for discussing plane waves. So it just has this single equation, and there's the pressure and the saturation. But we can actually eliminate the pressure in the water because here's the total velocity. It is just a constant, and we're in one dimension, say along the x-axis. And of course, it should be a function of t, but we'd have to rescale if it were evolving with time. So here's the expression for the total velocity in terms of the variables, and we can eliminate this term dpdx in terms of everything else. So we get the capillary pressure, and then everything, and then the various mobilities. All right. So the equation becomes the classical diffusion equation of this form, where the flux function is this from this term, right? I've got a lambda times dp dx, so it looks like this, and the h of u, this constant, this function, like a diffusion function, in front of dp dx has this form. So I've just done a little bit of algebra here.
Well, again, however, both of them vanish at 0.
Yes,
It's lambda
and a 1.
Yeah.
Well, yeah, so h vanishes at both 0 and 1, and f looks like this. So here's that same equation. Here are the same formulae, the fractional flow rate, the dissipation coefficient. And so we could write the lambda minus little lambda actually is just the oil mobility. And we get this shape for the function. So here I've chosen some constants. I've chosen the mobilities to be quadratic. And we also always get an inflection point. There are general results, of course. And h of u has a unique maximum and is 0. At the endpoints, it doesn't actually have to be flat at the ends. All right, so what to do about this capillary pressure? So the Buckley-Leverett approach was ignore it. It's a higher order effect. It will just be smoothing. So they looked at the scalar non-convex conservation law, and because because F is not convex, you need a Lax-Olenek construction, a rarefaction shock interface. So that's their classic solution for water displacing oil. You go from U equals 1 to U equals 0, and I'll show you the structure of that wave in a little bit. We're still at the introductory stage. So the classical approach was to use the equilibrium pressure, a decreasing function, get a degenerate parabolic equation. There is a maximum principle, so U is pinned between 0 and 1 if it starts off in that physical regime, so it's positively invariant. And the only difference with the capillary pressure is that the Lax-Olenek solutions get replaced by a smooth approximation. So it is actually quite benign, including the parabolic term. In the Hassan-Azadeh and Gray model with this rate dependence, we get a bigger equation. We have this extra term, and it has that xxt derivative. So it's a little like a BBM Burger's equation. Here's a modified BBM Burger's equation. There isn't a maximum principle, but Fan showed that the physical interval 0 to 1 is still positively invariant. And right, so my students actually studied the simpler system where you can actually write down formulae for traveling waves for undercompressive shocks.
Is tau less than 1?
What was the question
Is
again?
tau less than 1?
Tau could be anything. In fact, actually, we're taking it anywhere between 0 and infinity. Right? So, of course, if tau goes to infinity, you want to rescale to get this term dominating and eliminate the dissipation. So tau is like a ratio between alpha and the square root of beta. All right, so the constructions for this equation actually are similar to the modified KdV Burger's equation that I studied with actually a master's student in '95 and well documented in the Flocks book of 2002. All right, so let's look at traveling wave solutions of the full Hassan-Azadeh Gray equation. So the ansatz is that U is a function of x and t in the traveling wave frame, and we substitute into the equation and get a derivative of every term. So here's the t derivative, and these terms all come from x derivatives, except for this last one, which picks up a tau, which picks up an s because it has a t derivative. So we can integrate once, use boundary conditions, say at minus infinity, and we get this second order ODE, which is degenerate because h is 0 at u equals 0 and 1, and two parameters, u minus and s. It's convenient to rescale the independent variable with s and tau, and we can write the second order equation as a first order system. So it's singular at u equals 0 and 1, but at least we've got something definite to work with. So here are typical phase portraits. We're going to look just in a regime where there are three equilibria. So the three equilibrium, maybe I can draw a little sketch. We'll need that in a minute. So here's the flux function F. And we're going to have three equilibria like this. So I think, right, I've got U minus is small, U plus is near 1, and then there's a middle equilibrium, which I call U mid. Okay, we'll call it UM. Okay, so the slope of the chord is actually the speed of the wave, and the three intersection points correspond to the equilibrium. So I've got U prime is V vertically and U horizontally from 0 to 1. So the point of these three pictures, which are typical of the phase portraits you get, apart from some symmetries, is that we have the middle equilibrium is always an unstable node, or a spiral. In this case, it's a spiral. And we have two saddle points on the outside. So in this case, we have the middle equilibrium connected to U minus, so that actually corresponds to a lax shock, satisfies the lax entropy condition. And the unstable manifold here in red is above the stable manifold going to U plus. We can, by varying a parameter, say by varying S or U minus, we can reverse that order. And here I've got a separation function, actually evaluated at middle equilibrium, which would be positive here and negative here, by continuity somewhere in between at 0. Okay, so when that separation function is 0, we have a saddle-to-saddle connection, a codimension 1 vector field. Okay, and that's associated with what we'll call an undercompressive shock. And I'll explain a little bit in the hyperbolic theory what that means. All right, so that gives us a numerical procedure. If tau is finite, we just fix it, fix U minus, and then find U plus just by finding zeros of this separation function. We can actually show that we have monotonicity of this function of U minus by using a Melnikov integral. That's a technique from dynamical systems. So that tells us the sign of derivatives of R. For tau equals infinity, when the dispersive term dominates, we can determine just from an exact integral. Actually, we have a Hamiltonian system, and so we get a connection exactly when some integral is 0, and we can analyze that directly without using the separation function is essentially this integral. So it is important. I didn't mention what M is. I realized it's a mobility ratio, but we can analyze the asymptotics in the corners. Because the corners U equals 0, U equals 1 are degenerate points, we can't analyze the vector field there. It doesn't make any sense. But we can look at the asymptotics and find that actually and again, I didn't specify the form of the mobility functions, but this M is a mobility ratio, and we get this power law in the corners. So that allows us to analyze how these U minus and U plus line up to get the undercompressive shocks or these traveling wave saddle-saddle connections. So here's a sort of a quick idea of how the algorithm goes. We know that for U plus small enough, fixed U minus, say at 0.4, R is positive, and near this top boundary where U plus is near 1, R is negative, so we can just do a simple interval division to get this the set of points where there's a saddle-saddle connection. So this is for tau equals 0.1, and here I've shown tau equals 0.1 in blue. This is now on the full interval. There's a piece up in the left-hand corner, top left-hand, and also a corresponding piece in the bottom right-hand corner. The inflection point is right here, and all of these saddle-saddle connections occur between the green line and the dotted line. And I won't waste time explaining what the various constructions here are. All right, so let's go interpret this in terms of the scalar conservation law. So I need to remind you a little bit about constructions here. So there are rarefaction waves, which are continuous waves that connect a constant u minus at small x to a constant u plus at larger x, and in between we get a self-similar function which is continuous at these two endpoints. And then shock waves. So notice that the characteristic speed f prime has to increase from u minus to u plus. So that's like a side condition on the rarefactions to make so that this makes sense. And shock waves are jumps from u minus to u plus at a speed s, and there we have to satisfy the Rankine-Hugoniot condition, which I also I mentioned just now. Okay, so here's the difference between lax shocks and undercompressive shocks. So a lax shock satisfies this pair of inequalities. The characteristic speed has to frame the shock speed in this way. So sound waves ahead of the wave move more slowly than the shock. Sound waves behind go faster. So signals are converging on the shock from both sides. And graphically, we can see this in the flux function. Here's the same sort of chord that I just drew between two equilibria, and the slope of the chord is s. The slope of the tangents are the characteristic speeds. Okay, so this is a lax shock. And an undercompressive shock, not only, and I should mention that we'll say that lax shocks are admissible only if there is a connection from u minus to u plus. And actually, some of these lax shocks are not admissible according to that criterion. An undercompressive shock, you have the chord actually cutting so that the slope is on one side of the two characteristic speeds. So signals go through an undercompressive shock. But we also insist that there's a traveling wave. Okay, so now we want to solve the conservation law. Here's the Buckley-Leverett solution, the rarefaction shock construction I mentioned. So you want to go from 1 to 0, from water to oil, and you put in a rarefaction wave, a continuous wave in green, and then a shock down to all oil. So that's that sort of mushy region, the intermediate region behind the interface. And we can generalize that to have a jump from any left state to any right state. This is a classical construction using only lax shocks, not necessarily admissible shocks. And so this is like a phase diagram for the solution for any UL and UR coded by shock, rarefaction, and the Buckley-Leverett construction rarefaction shock. Their solution, of course, is way down in this corner. All right, so if you have dynamic capillary pressure, it gives you a different story because we saw these other phase diagrams, these other phase portraits. And so the rarefaction shock region and the shock region get split up, and you have these additional waves. So it's somewhat more complicated. And let me show you some simulations. So these are the classical waves. Now we're doing PDE simulations of the full equation. And I'll show you all four types of waves. So here's a rarefaction wave going from the left state to the right state, continuous wave. Here's a lax shock. So we've got the smoothing. So of course we get some smoothing of the shock. And here UL will correspond to an unstable spiral. That's why you get oscillations. And then if we look at solutions with non-classical waves with undercompressive shocks, here's a UL to a higher level. So we started with a monotonic initial condition. It finds this plateau, and then this shock, the undercompressive shock, which is a large feature, is traveling faster than the weak shock, which is the lax shock behind. And here's the corresponding thing with a rarefaction and a faster shock. So the neat thing about this is you get two waves for a scalar conservation law, which is by now, reasonably well understood, but still sort of surprising. All right, so there's another thing that I didn't mention, that I was typically looking at quadratic relative permeabilities. There are actually two classes of permeability, and here I want to show you just some examples of what are called sharp traveling waves. where the permeabilities have some fractional power. I'll take the 2 powers
Before you do
to
that,
be
can I
3
ask
halves.
something?
Yes, yes,
Because
of course.
it goes fast.
Yeah.
So the speed of the traveling wave is the speed of the shock, so there is no...
Yes. Yes, so this, of course, this is not exactly a traveling wave, but it's approximately a traveling wave. And it travels with the predicted speed from the Rankine-Hugoniot condition between these two things.
What do you mean
Yeah.
approximate?
So-
So it's not a traveling wave, so you compare...
Well, the only reason it's not a traveling wave is that it doesn't extend all the way to plus and minus infinity.
Well,
These are numerical solutions.
I know.
Right.
No, but analytically it would be actually extending to infinity like this and traveling with the speed of shock.
If you just looked at the traveling wave, yes.
Yes.
Yes, right, yeah. But the PDE solution, of course, is only approximately given by a superposition of traveling waves. Yeah.
So I guess since we're only looking at the variable u, which is the volume fraction or concentration fraction?
Right, it's saturation, the volume fraction.
Yeah.
Yeah.
There's no analog of contact discontinuities, right?
No,
No?
not in this problem. Right. You can in the rarefaction shock, it's a one-sided contact. That the leading edge of the rarefaction wave is the shock speed. So the shock is actually characteristic on one side. So that's not a contact discontinuity. Yeah. Yeah, and then okay. So maybe you're thinking of the Euler equations, but in particular we have incompressibility here, and we're not writing down conservation of momentum, except through Darcy's law. Okay. Yeah. So I just wanted to mention that the Netherlands group actually identified a different sort of traveling wave, and in their numerical simulations, but we can actually analyze them as well. So these are traveling waves which have a corner at u equals 1 or at u equals 0. And so for these particular relative permeabilities, we were able to compute PDE solutions with an initially a monotonic profile, which evolves with oscillations somewhat similar to what we saw with the undercompressive shocks. And then we just get this pattern with a faster wave, which is singular at u equals 1, but resembles an undercompressive wave, and then a lax shock behind. So this is stable under mesh refinement. And if we look at the corresponding phase portraits, and there's a slight mismatch in the numbers used here, but try and ignore that. There's a spiral to up to u plus equals 1. So this is a classical shock or limiting lax shock profile to a degenerate equilibrium. And then we have this sharp shock, which actually has non-zero speed, right? So v is negative, non-zero slope, I should say, at u equals 1, and then goes down to the other equilibrium, which is invisible here because it's a 0.025. Okay. Right, so let me switch to discuss stability of, and I'm only going to discuss stability of lax shocks. And this is all at the hyperbolic level, seeming hyperbolic level. And this is somewhat analogous to the Safran-Taylor analysis for Healy-Shaw cells. They actually, at the beginning of the paper, looked at two-phase flow problems and wrote down a criterion in terms of mobility ratio for fingering instabilities. So their context was to go from 1 to 0, water displacing oil, and discuss the stability of the planar shock. So we actually know that the planar shock is not hyperbolically stable even in one dimension. It should be replaced by the Buckley-Leverett construction, the rarefaction shock. But aside from that, we want to do the full problem where we have a jump from one saturation to another saturation. Okay, so that's the story I want to tell you at this hyperbolic level. So the context is there's an interface which moves with constant speed s, the velocity given by, on each side given by Darcy's law with the mobilities, a continuous pressure which is increasing or decreasing on each side. So it's linear in x minus st, just comes from these equations, v plus and minus a constant. And we have the shock speed in terms of the saturations, as usual, and the lax condition. So now we're going to introduce the second variable, y. We wrote down equations for that, for two-dimensional flow, and they look like this. So there's no capillary pressure, so the equations still have U and P, the saturation of water and the pressure of water, as the unknowns. And there are now really two equations. We can't eliminate P by manipulating Darcy's law. So these are the two equations, one evolution equation and then the incompressibility equation. So we have jump conditions for this pair of equations, but if the interface is a function of y at each time t, then the normal is given in space-time by this expression. And so the jump condition just says that the normal component of the vector fields in space-time should be continuous. So here I've just taken the dot product of this normal with the corresponding flux function here, the jumps in the variables. And similarly, for the second equation, we get a jump condition. Okay, so we've got states on a base shock, which has states on either side, pressures and saturations, and we've also got a speed. This v should be an s. Okay. So of course we want to linearize. We're just going to look at linearized stability, and when we linearize, so here are the original equations. I carry out the derivatives, and then it's easy to see how the linearization works. Okay, so we perturb the saturation, we perturb the pressure, and write down the linearization. So I get, in particular, a Laplacian of this perturbation, capital P, and U comes in the obvious way. So the bars, remember, are the underlying shock. So we can eliminate the Laplacian of P, right, from this equation in terms of du dx. If I do that, then we get a scalar, a linear equation with constant coefficients on each side. Right, so capital U has to satisfy this linear transport equation on each side. So I claim that means that capital U has to be 0. So that this is the sort of key step in doing the analysis of this problem. So here's that equation again, that linear equation of capital U, and it's on each side. So U bar is either has a plus or a minus, and we need capital U on each side. So you make the usual ansatz that capital U is a function of the longitudinal variable. We're in a moving frame here. The transverse variable, so an oscillation in the transverse variable, and then a growth rate or decay rate of sigma, which could of course in principle be complex. And so we'll write prime as the ordinary derivative in this moving frame, and substitute into the equation, and we get this ODE. Okay, so we analyze the ODE, has constant coefficients, so we can do everything, and we get so there's some simplification by recognizing that the flux function is buried in here, and so we can reduce this ODE to this form. And notice that this is going to be relevant for lax shocks. It has one sign or the other on each side of the shock, right? The shock speed is either bigger than or less than the characteristic speed. So we have exponential solutions, and we want to know whether these grow or decay at infinity. We're looking for bounded perturbations, so they mustn't grow. And so that's the point here. So you substitute in, you get an algebraic relation. We know the sign of this term. If sigma has a positive real part, then we know the sign of beta plus minus, or the sign of the real part of beta plus minus. And we don't want it to be positive for Z positive or negative for Z negative. And the lax entropy condition guarantees that actually it grows on both sides. So W must be 0, and so that U must be 0. So I didn't state it as a theorem, but that's the proof. All right, so now we've reduced the problem just to analyzing the perturbation in pressure and the perturbation of the interface. So there's a variable, a number A here, and then a function, capital P, which again we'll write in this usual form with a growth rate and a sinusoidal perturbation and a coefficient that depends on Z. We substitute in and we get linearized equations. In particular, we have the Laplacian of p is 0. We already satisfied the other equation because with having capital U equals 0. So we just need the Laplacian of p to be 0. We get a second order equation, and we know what solutions look like. Alpha, the wave number, will be positive. We'll choose it to be positive. And so we want the exponentials to decay at plus or minus infinity. And we need to determine these two coefficients. So we've actually got three coefficients to find. And we find them by linearizing the jump conditions. This is usually done in hyperbolic theory. It's done with incredible amounts of notation. And part of the point here is that it's so simple, and it really mimics the Taylor-Sackman analysis in that very simplified context of water going to oil. But it's not much more complicated aside from the previous transparency in this case. All right, so here are the linearized jump conditions. Here are the jump conditions. I've put in the fact that capital U is 0. So we only have Q and A, actually, and Q is related to B plus and B minus. All right, so the second equation is easy to interpret. The minus sign comes about because we have a plus minus sign in the exponential, and I had to differentiate Q. So that's the explanation of that minus sign. And then using that information in the first equation, we get an equation. Here's sigma popping up on the right-hand side. We get this equation from that linearized jump condition. And recognizing that these terms, again, combine to give a shock speed, we get this rather simple expression which relates B minus to A. So we've also got B plus. So now we've got two equations, three unknowns. We need a third equation. And the third equation is just comes from imposing continuity of pressure. So here's the expression for the pressure. We just make it equal at z equals 0 on each side, and we get this third equation. Okay. All right, three equations, three unknowns, completely linear. The determinant has to be 0 to get a non-trivial solution, and that turns out to be this expression. So this is entirely analogous to the Sackman-Taylor expression. Sigma is linear in alpha because we're at the hyperbolic level. There's the scale invariance. And the shock speed is involved, and then the total mobilities on each side. So the denominator here is positive, and stability is controlled by the numerator. Okay, so here's a graphical interpretation. So this picture actually is from MATLAB, and with quadratic permeabilities, but you can put in other convex functions. So rather than going through all the bits and pieces, let me just give you the pictorial version. So the green shaded area is where we have lax shocks, so U minus and U plus. And they can be either stable or unstable. Weak lax shocks, where U plus is close to U minus, is on this diagram. And so weak lax shocks can be either stable or unstable, which is kind of surprising. And we tested this in the full equation with dissipation and dispersion with numerical methods. So we put in a plane shock, a plane interface, and perturbed it with, in this case, just with some noise, and look at the evolution. And yeah, actually, right, that's right. And so now I'm going to show you blown up versions of that. So here's the stable case. So here's the data. U plus is 0, and U minus is pretty small, like 0.25. So we put in a hyperbolic tangent to approximate the plane interface. We put in a particular wave number, a particular sinusoidal function, and then we superimpose some noise. So notice I've zoomed in here quite a bit so you can see what's going on. The high frequency noise dies away on a fairly rapid time scale, and then because this wave number is in the stable regime, it just approximates the shock. And again, we're in a moving frame here, so it collapses to 0. In the unstable case, so here I've got the same U minus and moved U plus up, so we're unstable. similar initial condition, and this time that unstable wave number grows. So it's, we didn't probe precisely this boundary between stable and unstable, just to illustrate how this works. Okay, so this is a quick summary. There was a more sophisticated stability analysis done by Cialeppi and co-workers, no, by Hesse. I'm forgetting, I had it on a previous version of this. So it's Cialeppi who did the numerical simulations. There was a very complicated matched asymptotic analysis, including dissipation terms. There was also established criteria for stability, but didn't really explore in terms of the lax entropy condition. So here's a sort of funny punchline that if you have an oil-water mixture displacing oil, then the interface can be stable. I'm not proposing this as a solution for the petroleum engineers, because that would be a hard thing to arrange, but it's kind of interesting that here's another stability mechanism. If you have rate dependent, another stability mechanism, just looking at the hyperbolic level. Okay, so I have, what, 10, 15 minutes? Judah, you're in charge, right? I can talk all afternoon, is that okay? We'll skip lunch. Okay. So I wanted to just mention very briefly a different approach to porous media, which involves displacing water with air in a capillary tube. So we'll write a similar equation, but this time we're going to have a phase field model. So this we'll have this function psi, which is the variational derivative of free energy. The free energy, as usual, is split up into a bulk free energy and an interfacial energy, but there will also be we need to have this extra coefficient, which is we'll call the interfacial energy weight. We'll use the corresponding fractional flow rate, not for oil recovery, but for air and water. There are various parameters that will show up, and the key one is the capillary number, which is a balance between surface tension and viscosity. Here's the ratio with a typical velocity, capital U. The saturation here is an area fraction, right? So we take a cross section, say in this location, and the water cross section, we're assuming axisymmetry, is circular with a radius little r, and the radius of the capillary tube's capital R. So the area fraction is r squared, little r squared over capital R squared. It'll be a function of x and t. Okay, so the specific model that was proposed by Cueto, Felgaroso, and Juanes in a couple of papers had this typical double well potential, a straightforward function rather than involving the more thermodynamically based double well potential. And right, so there are various surface energies involved here, and we're going to assume that the spreading parameter is negative, so that we can actually get spreading at the interface. We have to have consistency with the Young-Laplace law. That's this equation, and then the interfacial energy takes this functional form. So as usual, the gradient squared is involved, and we'll have a coefficient that depends on the contact angle. So when we do the calculation, calculate the variational derivative, and do some messing about, somewhat mysteriously, you get the square root of kappa comes out. So it has this rather nice form. Here's just the derivative of that double well potential, and then this is from the other part of the variational derivative. So there are similar models for polymer mixtures. I mentioned some references going back to De Gennes. My colleague Tom Witelski had exactly this model, and then there's a recent paper on binary fluid mixtures in PRL. Here's the whole equation written out. And h of u actually is the same as it was in the previous part of the talk, the fractional flow rate and then mobility. So q of u changes sign. So this is destabilizing for u in a certain interval between 0 and 1. Okay, so I haven't told you about kappa of u, so this is the first little contribution, that we can determine kappa of u with a very sort of inverse argument, a very simple inverse argument. We assume that if we've got a stationary bubble, that the ends are spherical, so spherical cap solutions for a bubble. And then, so we know the solution out here, and so then we should be able to determine the kappa that gives you that stationary solution. So of course we get a fourth order equation for stationary solutions, but we can go through and replace x by u everywhere, get an ODE for the square root of kappa of u, which we can solve explicitly. Here I'm assuming the contact angle is 0 or pi, but there's also an argument when you have a general contact angle, and the form of kappa of u is like this, depending on the contact angle. In fact, you don't even have to have the specific constitutive law that I wrote down. You can have a rather general bistable G of U. Okay, so we did PDE simulations, and so did Juanes and Cueto Filgaroso, and they also found this sort of structure. This is a highly dissipative system, but what you see is something rather hyperbolic. You see something that looks like a rarefaction wave, broadening, and you get a plateau, and then you get a sharp jump down to essentially 0. In the engineering simulations, they actually had the code cut off the simulations at u equal when u got close to 0. U equals 0 is a singular point, as it was previously, but I want to show you that actually you can analyze this situation. Okay, so traveling waves. So this is very analogous to the first part of the talk. So we look at the full PDE, we put in the traveling wave ansatz with boundary conditions at minus infinity. We want u to go to 0 at some finite point, let's say at u equals 0. So at x equals st, at x equals st. So that in that case, the shock speed is just f over u on the left. Here's the ODE having integrated once, and the constant integration is 0 because of this relation, and we can write as a first order system in the usual way. But we get these functions m of u, the square root of kappa of u, which are 0 at u equals 0. So it's a singular system of ODEs at u equals 0. But we can eliminate m of u because on the right we've got a vector field, which is not singular at all. So we do that. We change variables. So depending on the solution, we change independent variable. And then you get a system of ODEs that you can analyze on the whole line in this new variable, eta. Okay, so we can do that. And let's see. So there are some constraints here that if you're not careful, u can go negative. Right? The u equals 0 is now in equilibrium, and it's an attractor. It has a two-dimensional stable manifold, but you can get u changing sign on that stable manifold. So you need a restriction on the capillary number. So then the two-dimensional stable manifold is a stable node, and we can find traveling waves. So my student has been doing computations, and when you convert back, so this is just an example of a traveling wave calculated in the whole line, converted back with the using this formula, this change of variables depending on the solution, and here's the traveling wave coming down to 0 at a finite point. So this is sort of preliminary work, and we need to verify these structures with our own PDE simulations. But so far we have good agreement with the engineers. All right, so just as a quick 1-minute summary, there are many applications of two-phase flow in porous media. And in the oil recovery context, we looked at lax shocks, which can be stable or unstable to two-dimensional perturbations. Oh, here's that reference I was thinking of. The Yortsus and Hickenel actually studied traveling wave stability for the full equations with dissipation and dispersion. And it's a very hard, in fact, there's some doubt as to whether their analysis is really correct. They're very hard matched asymptotic analysis with all sorts of changes of variable. We found a simpler way to analyze stability at the hyperbolic level. And then I showed you the beginnings of a different approach to porous media, which involves phase field theory. And I also mentioned about sharp shocks, showing you some simulations. Good. Well, thank you.
Questions, comments?
But this relaxation term in the first model, this relaxation term in time, I mean, what is it physically? Some local coarsening of bubbles? Or I mean, it changes capillary pressure, what is already in...
Well, the pressures are evolving. So if the capillary pressure is just the jump across an interface, then it should also be evolving. But you expect bubbles to equilibrate on a fast time scale. So that's what the tau is about. That's the thinking behind the relaxation.
Relaxation in shape, but keeping its size, their size? Or
Well,
bubbles?
the saturation is evolving as well. Everything is evolving. But in the original model, the time dependence of the capillary pressure was ignored. So that if you have a certain saturation, you have a certain capillary pressure. So it's assuming, thinking of an array of bubbles and having a jump in pressure, and you average. But if the bubbles are evolving, so this was the point of Gray and Hassanizadeh, that there should be some time dependence, and this is a simple way to put it in.
Can I
Yes.
ask about the phase field analysis for flow in a capillary tube?
Yes.
Previously you had talked about a porous medium and you've
Right.
got a continuum model. Now I'm not clear whether you've got a continuum model in any sense involving a capillary tube or whether you've got two separate phases.
Right. So the thinking here is that if you think of a porous medium, this is a very old idea, that you think of a porous medium as being consisting of very thin tubes, capillary tubes, with some, tortuosity, I think it was called classically. And then in each capillary tube, you will have, in this case, gas displacing water. And then this saturation makes sense, because when you average over the entire medium, then you're taking a sum of these, an average of these saturations. So that would be the local saturation. Or if you average over
I
volumes.
don't see any reference to how you'd averaged over a lot of capillaries, because the key issue that you were talking about
Right.
was the effect of the contact angle at the actual interface between the solid phase
Yes.
and the two liquid phases.
Right, that's right. And
So I must have missed something, or you didn't tell me something.
I probably didn't tell you, but what was it? So it does depend on that contact angle. Yes, the modeling does depend on the contact angle. This is not, this model actually, it's an interesting feature that it does not apply in the Bretherton context. So the Bretherton context was where you have an air bubble surrounded by water, and the gap between the air bubble and the sides of the capillary tube is very small, so you can use asymptotics to describe the speed of the air bubble relative to the surrounding fluid. That's a different problem
Yes,
from this.
I wasn't going to introduce Bretherton. No.
No, but actually it was my early question with this model. Can you recover the Bretherton analysis with this model? And you can't. That's not the point. The point is having a fluid that is attached to the side being displaced by another fluid. Yes.
So building on that, you have a contact line singularity at the surface, and I'm missing what alleviates that contact line singularity.
The contact line is not moving in the Young-Laplace law, so there's no
So you're not. Oh, okay.
there's
so
no
you're not
singularity in the pressure. Is that what you mean?
No, I assumed that you'd have your interface moving down a capillary at some stage.
Right. So this is a finger of air that's moving down the capillary tube.
So the actual interface is staying put, but the contact line.
The
Is
contact
staying put,
line
and
is
it's
staying
just being
put.
pushed there.
Right.
So how does that square with the porous medium picture, where you've got, I assume, interfaces advancing?
Right. So again, this is something that is buried in the classical literature of how you model a porous medium, flow in a porous medium of two fluids using capillary tubes, so that all of the displacement takes place in that way. You have a finger of something that's propagating into of one fluid propagating into the other fluid. So if you think of just an array of, right, so if you just think of an array of capillary tubes or an array of tubes, and in each tube, of course the tubes have different widths, in each tube you have one of these fingers, and they've each propagated to a different extent, then you get a saturation that depends on position.
And I mean, there is some physics missed out there because the
Oh, there's
contact
tons
line
of
is going
physics.
to move and there's going to be diffusion,
course.
which is going to make it.
Right, so they actually have a two-dimensional model, and they're testing against experiments. So the pictures I showed you of the tube are the experiments at MIT. And they've checked their PDE simulations against the experiments. So in that limited context, there seems to be good agreement between the model and the experiment.
Thank you very much.